Okay, so we are going to start talking about reaction mechanisms. We introduced this a little bit in Unit 3 when we talked about free radical substitutions, but we're going to do a lot more with mechanisms in Unit 10. So today we're going to focus on nucleophilic substitution reactions, and we're also going to talk about condensation reactions. You don't need a mechanism for that, but you do need to be able to predict the products. Okay, so a reaction mechanism basically shows us how the reactants turn into the products. We talked about this a little bit in Unit 6, right? So when we look at an overall reaction, we just see the reactants of the products. We don't see how we get from point A to point B. In organic chemistry, we're going to show reaction mechanisms using curly arrows to show the movement of electrons. So anytime you draw an arrow, you're showing how electrons move from one place to another. Okay, so a couple of important vocabulary words you need to be aware of for mechanisms. A nucleophile, if you break down the word, means nucleus loving. So this is a species in this case meaning atom, ion, molecule, that contains a lone pair of electrons that's donated to an electron deficient center. So basically it's attracted to something positive or electron deficient. So a nucleophile is just a Lewis base, right? An electron pair donor. And this will form a dative bond. An electrophile is the opposite, electron loving. And this is an electron deficient species that can accept an electron pair, so a Lewis acid. And when it accepts that electron pair, again, a dative bond will be formed. A leaving group is just what it sounds like, an atom or group of atoms which breaks away from a molecule during a substitution reaction. And a carbocation, this is kind of an interesting thing, we haven't really seen this before, is an organic ion with a positive charge on an electron deficient carbon atom. And this is the intermediate in an SN1 reaction. Okay, so nucleophilic substitutions occur when one nucleophile substitutes for another nucleophile. We're usually going to see these when a halogenoalkane reacts with another nucleophile like hydroxide, ammonia, or cyanide. Now, because the carbon-halogen bond is so polar, the carbon will get a slightly positive charge. Because remember, when we have a carbon-halogen bond, when we drew that arrow, that shows the direction that electrons are being pulled by the more electronegative atom. So then the carbon would get a slightly positive charge, which attracts the nucleophile. Okay, so the first type of reaction we're going to talk about is an SN1 reaction. And in SN1, the S stands for substitution, the N stands for nucleophilic, and 1 stands for unimolecular. So what that means that it's unimolecular is that in the rate determining step, there's only one reactant. So in this case, the halogenoalkane is involved in the rate determining step. Okay, since it's unimolecular and only the halogenoalkane affects the rate, if we were to write the rate law for an SN1 reaction, it would look like this. Rate equals K, the rate constant, times the concentration of the halogenoalkane. This is going to occur with tertiary halogenoalkanes, and I'll review that in just a second. And again, we're going to represent movement of electrons with arrows. Well, so a tertiary halogenoalkane is when the carbon that's bonded to the halogen, in this case bromine, is bonded to 3 other carbons. Okay, so that's an example of a tertiary halogenoalkane. If this were a hydrogen atom, it would be secondary, and if there were 2 hydrogen atoms, it would be primary. Okay, so let's look at an example of an SN1 reaction. So we're going to show this molecule reacting with hydroxide. Okay, so first let's draw our molecule. And I'm going to draw the methyl groups here condensed, just because it's a little bit easier to see what's going to happen. Okay, so I have my molecule. Just as a nice review, the longest chain is 3 carbons. So this would be propane. It would be 2-bromo, 2-methylpropane. Okay? All right, so it's going to react with hydroxide. And so the net effect of this is that the bromine is going to be substituted with a hydroxyl group. So in an SN1 reaction, the first step only involves one molecule, the halogenoalkane. So the first step is that the leaving group is going to leave. Okay, so when I draw my arrow, I'm going to show that the electrons in this bond are going to bromine. Okay? This is an example of heterolytic fission. You might remember when we talked about the free radical mechanism that had homolytic fission, where both of the atoms were getting one of the electrons from the bond. This is heterolytic fission, so bromine is going to get both of the electrons. Okay, so we're going to form a carbocation intermediate where the carbon is going to have a positive charge. Now, you've never seen a positively charged carbon atom before, and that's because, well, they're not really particularly common. Okay? This is really not very stable. So what's going to happen is that my nucleophile is going to attack that carbocation. So the electrons in this lone pair here are going to be attracted to that positive charge. So I'm going to draw an arrow from those electrons to the carbocation, showing again that the movement of electrons. And this is going to form a dative bond. So in the end, this is what we have. Okay? Now, it's also important to note that in this reaction we did lose the bromine atom, so we produced a bromide ion. So it's important that you still show that as a product in the end. All right? So this is our SN1 reaction. We had a nucleophilic substitution, so that's the S and the N, and it was unimolecular, because in the first step there was only one molecule involved. Okay, let's talk about SN2 reactions, and there's some sort of specific things we need to pay attention to when we draw these, so this will be a good one to practice a lot. All right, so in SN2, again, the S is substitution and the N is nucleophilic. The 2 means bimolecular. So in the rate determining step, there are 2 species involved. So in this case, that would be the halogenoalkane and the nucleophile, whatever that may be. Okay, so if we were to write a rate law for this, we would say rate equals K times the concentration of the halogenoalkane. That's a long word, isn't it? Times the concentration of the nucleophile, whatever that is. And this is going to occur with primary halogenoalkanes. There's 2 main reasons that SN2 happens with primary halogenoalkanes and not with tertiary. The first reason is that in a primary halogenoalkane, the carbocation is not stable. So in the tertiary halogenoalkane, like the one we just saw, that positive charge is actually shared between all of those carbon atoms. So it's sort of distributed through, between the neighboring carbons, which stabilizes it a little bit. Additionally, in a tertiary halogenoalkane, these bulky methyl groups create steric hindrance. So they kind of are blocking the carbon from being attacked by the nucleophile until something's left. So with a tertiary, the leaving group has to leave before the nucleophile can even attack. SN2 reactions form a transition state. So in SN1 we had a carbocation intermediate. This is going to form a transition state, and I'm going to show you how we show that exactly. And this is slower than an SN1 reaction. Okay, so let's look at an example with 1-bromoethane reacting with hydroxide. Okay, and it's also important to note sometimes this might be saying that it reacts with potassium hydroxide or sodium hydroxide. The potassium there would just be a spectator ion. It's not important. Okay, so we're going to draw 1-bromoethane. And I'm going to draw it where the second carbon is actually condensed. Now, you notice that when I draw 1-bromoethane that I'm using the wedges and hash marks to show the geometry. So remember that the solid wedge means that that methyl group is sort of coming out of the plane of the board, and this hash mark around the hydrogen shows that it's going backwards. Okay? And it's important that we show the stereochemistry in this particular case because something interesting is going to happen in an SN2 reaction that doesn't happen in an SN1. Okay, so in step 1, the nucleophile is going to attack. So I'm going to draw my nucleophile, and this is a little crowded. Okay? And I'm going to show the nucleophile attacking. Now, An interesting thing that's going to happen is that it's going to attack on the opposite side from the existing nucleophile. And that's because the existing nucleophile, the bromine atom, provides some steric hindrance which sort of blocks attack on that side. Okay? So this is going to create something kind of unique, which is a 5-membered transition state. So carbon is going to have 5 bonds here. Oh, sorry, that looks kind of ugly. And basically it's going to form these sort of temporary bonds with the hydroxyl group and the bromo group. Okay? So this is a 5-member transition state. Now, remember that hydroxide has a negative charge. So since that has now been added to 1-bromoethane, this overall transition state will have a negative 1 charge. Okay, so now that we've formed our 5-membered transition state, the leaving group is going to leave. And this is a very fast step because these partial bonds to carbon, it's a very unstable transition state. Okay, so we're going to show the movement of electrons. Again, it's heterolytic, so both the electrons in that partial bond are going to the bromine. And when we draw the product, we're going to see that something interesting has occurred. Okay, so because of the way the nucleophile attacks, the position of the nucleophile is inverted. Sorry, this isn't drawing very clearly, but you can see that it's sort of, it's called the Wallen inversion. The idea is, think of it as like an umbrella that's turned inside out. Okay, so SN2 reactions are considered to be stereospecific. And we'll talk more about what that means when we talk about stereochemistry in the 3rd topic in this unit. Okay, but in the SN2 reaction, we do have an inversion of position. Okay, now, secondary halogenoalkanes can react via either mechanism. Because SN2 are faster than SN1, the rate of the reaction of halogenoalkanes is tertiary is fastest, primary is slowest, and secondary, which reacts via both mechanisms, is somewhere in the middle. Now, another factor that affects the rate of these reactions is the identity of the halogen. So since bond strength decreases from chlorine to bromine to iodine with carbon, iodoalkanes are going to react the most quickly, and therefore we would consider iodine to be a very good leaving group. Now, there are solvents that are more ideal for SN1 versus SN2. So SN1 is best conducted in polar protic solvents, and protic coming from the word proton, so that means providing a hydrogen. A good example of a polar protic solvent is water. And the reason that these work well for SN1 reactions is that the polar protic solvent basically solvates the nucleophile and forms hydrogen bonds with it. So this prevents the nucleophile from attacking until we form the carbocation intermediate. In an SN2 reaction, these are best with non-polar aprotic solvents. So for example, propanone. And these solvents can't form hydrogen bonds with and solvate the nucleophile, but that's a good thing in this case because it leaves it free to attack and form the transition state. Okay, so we're going to do some practice problems. I would encourage you to try these on your own and then come back and check them. Okay, so pause for a second, then try it. Okay, so first problem is 2-bromo-2-methylbutane reacting with hydroxide. So the easiest way to figure out if it's primary, secondary, or tertiary is to draw it. And when I do that, I see that the carbon atom that's bonded to the halogen is bonded to 3 other carbons. Now, just for simplicity, I'm just going to leave those dashes to represent the hydrogens. It's just going to get a little crowded if I don't do that. Okay, so first, so this is tertiary, and therefore it's going to react via SN1. So remember, first the leaving group is going to leave. And we're going to generate our carbocation intermediate. Okay. And next, the nucleophile is going to attack. So our nucleophile, in this case, is hydroxide. So I'm going to draw an arrow from the lone pair of electrons to the carbocation, and I'm going to generate my product. And again, these are all hydrogens. We know this. I'm just going to leave the rest as dashes. Okay, so That's our first SN1 reaction. And again, it's important at the end to make sure you write that you've generated a bromide ion. I may have forgotten to do that in the last SN2, but make sure every time at the end you show the nucleophile that left. Okay, so go ahead and pause and try this one again. This is 1-chloropropane reacting with hydroxide. Okay, so this is primary, and we can see that if we draw it out. And I'm going to go ahead and draw this one again so that we're focusing on the carbon that's attached to the halogen. Okay, so I'm going to show using the wedge the rest of the carbon chain. Okay, all right, so first step is that the nucleophile attacks. Since it's primary, we know we have to be using SN2. All right, so my nucleophile attacks on the opposite side, and now I'm going to form my transition state. So I'm going to show my partial bonds to both nucleophiles. And remember, that has a -1 charge. And then I'm going to show my final product. The leaving group is going to leave. And remember, I'm going to have that inversion of position. So it's going to be just like an umbrella turned inside out. Now when I draw this, it's going to look a little bit strange. It's almost like I'm writing it backwards, and that's because I need to show that the carbons are actually connected to that bond. Okay? And again, I generated a chloride ion as a product. Okay, last one. 3-iodopentane reacts with cyanide. So here I told you to use SN1, and that's because it's secondary. All right, so it could react via either mechanism. Okay, and I'm just going to use these dashes to represent hydrogens because this is sort of a large molecule. All right, so first step in SN1, the leaving group is going to leave, and we're going to generate a carbocation, intermediate. And the nucleophile is going to attack. Now, this nucleophile, there's a lone pair on both sides, so it's not immediately evident where it's going to attack. But if you were to calculate the formal charge, you'd see that the negative charge is actually on the carbon. Additionally, it makes sense that the dative bond would form here, right? Because carbon likes to have, well, it doesn't like anything, but carbon is most stable when it has 4 bonds. So the nucleophile is going to attack from this side. And then we're going to get our final product, looks like that. And again, remember that we generated an iodide ion. Okay. So, as we just saw, other nucleophiles can substitute for halogens, not just hydroxide, through nucleophilic substitutions, such as a cyanide ion or ammonia. And when cyanide attaches to a carbon chain, it's called a nitrile group. So when it substitutes for hydroxide, if it substitutes at the end of the chain, because it contains a carbon atom, it will increase the length of the chain by 1 carbon atom. And substitution with ammonia creates an amine. Now, finally, we're going to talk about condensation reactions. We talked about these briefly when we learned about esters back in Unit 3 when we did naming. We're going to focus in on these a little more, and this is what the lab in 10.1 is going to focus on. So a condensation reaction occurs when an alcohol combines with a carboxylic acid to form an ester. And esters have a lot of uses in flavoring, scents, glues, plasticizers, lots of different things. And so when we say the word condensation reaction, we have to think about what does that mean? Okay, so what does it mean when water vapor in the air condenses? Well, it forms liquid water, like on the outside of a soda can. So a condensation reaction not only produces an ester, but it also produces a water molecule. So let's look at an example. 1-butanol or butan-1-ol reacting with propanoic acid. Now I'm going to draw the functional groups so they're pointing towards each other, just to show you how they come together. So butan 1-ol, I'm going to show, it doesn't matter obviously which way I draw it, but I'm going to draw it in this direction, reacting with propanoic acid. Okay, so when these come together, these two functional groups will come together to produce our ester group and then the water molecule. And so the product will look like this. And then, of course, all the hydrogens. Now, there are some conditions that are necessary for this reaction to occur. You need sulfuric acid and you need heat. So, to review naming esters, when we name them, we first name the alkyl group that's not double bonded to the oxygen. So this is the one that came from the alcohol in the original reaction. Then we're going to name the carboxylic acid part. So instead of saying ic acid, we're going to replace that with ate. So an alcohol that came from, or an ester that came from ethanol and ethanoic acid would be called ethyl ethanoate. Okay? And if we draw that, it would look like this. So this is the ethyl part, and this is the ethanoate part. Methyl ethanoate would look like this. So this is the methyl part that came from the alcohol. This is the part that came from the ethanoic acid. So when it says what ester would be formed from propan 1-ol and butanoic acid, we would call that propyl butanoate. Now, an interesting question that you might have to answer is to draw an ester that's formed from an alcohol where the functional group is not on the carbon on the end, so like propan 2-ol. Now, you would not have to name this product, but you should be able to draw it. So let's take a look. Okay, propan 2-ol and ethanoic acid. Okay, so this functional group and this functional group need to come together. So I'm going to label these carbons 1, 2, and 3 so you can see where they're going. So carbon 3 would then just be coming down here. Okay, this is sort of reminiscent of when we were drawing the polymers and we had to sort of consider what would happen with propene, for example. Okay? All right, so practice this a lot, especially with the mechanisms. The only way you're going to get good at this is by drawing them over and over and practicing them until it's just second nature.